Okay, so we're doing, I know this seems weird, it says chapter 1-7, this is the first section of chapter 2. Chapter 2 we start diving into properties now. Not just, vocab and some basic things like names of objects. That was kind of all chapter 1, or chapter 1 stuff. Chapter 2 is going further than that. Yeah, we're going to introduce some new words today, but we're going to get to major properties today. Stuff that on the next test, I'll have a bunch of formulas on the board for you, like a lot of them. So kind of be prepared for that. These are things you're going to want to use in the homework eventually. We might get a homework assignment as early as tomorrow. And so you do need these formulas because it will help you out. Okay? Alright, so first, let's talk about what we discussed yesterday. So is that Max? Perfect. Bane got out a little late. He forgot that it was 9 o'clock, didn't he? Mm-hmm. Yeah, it happens. Okay, so outline today. Yesterday we talked about what a polyhedra is, or polyhedron. We went through that definition. Polyhedra is plural. Polyhedron is singular. We'll talk about the faces again. We'll talk about the edges. We'll talk about the vertices. These all apply to the formulas, by the way. So that's why we need to know those things. But once we're through that was the stuff we did yesterday. We stopped there. We're going further. We're going to now talk about the specific types of polyhedrons. So there's prisms. We're going to talk about the pyramids today. We'll talk about any type of conic section, like a cylinder or a cone or a sphere. Those are the conics, the curved edges, and how they're different than polyhedra. But then the big thing is what I'm hoping to get to today. I don't know if we'll get to all of that. We might only get to maybe pyramids today. I have no idea. But whatever we get to, my goal is before, the end of maybe tomorrow, is to get to the idea of like all these special figures, the most special types of polyhedra, which is, they call them regular polyhedra, that's the term, or Platonic Solids. That's like the special name that they have. Platonic Solids are when you like go and buy a die for like a certain board game. They have that weird die that has all the letters on it for what is it? Not Scrabble. What is that one word?
Strategy.
Yeah. So bobblers. They have like weird die, right? Those are a Platonic solid. That die is made in a certain way that when you roll it, any number can pop up on the face because it's randomly made and it's just like it's perfectly balanced.
So for D&D, would a 20-sided die be like a Platonic solid?
Yeah, because it has to be able to land on any of those 20 sides perfectly. It's a Platonic solid, and we'll talk about those. There's only certain ones in this world that we have, and there's special faces to them. Okay, and then the goal today, and maybe tomorrow I should say, is talk about the formulas, like surface area. Surface area is kind of like in this room we have an area of like the floor. That's a surface area of this room. There's volume to an object if it's three-dimensional, because obviously we're talking about three-dimensional objects. Volume is like how much like space is in the room. So like how many desks could I stack in here total, that type of thing. And then the goal is to also talk about the generic formulas for the faces, like perimeter area of like each face. That's part of surface area. So, all right, polyhedra. This is the slide I think we had yesterday. So you should already have this stuff. I just want to review it one more time because we were kind of rushed yesterday. It was like right at the last part of class. Polyhedron, singular. Polyhedra is plural. But polyhedron is an object. It's a physical object or geometric figure that has flat surfaces, no curves now. Notice it has flat surfaces, and all those surfaces enclose a single region of space, a singular region of space. So the example I think I used yesterday was that why they say it has to be a single region. There's that, I think I used an example like, there's this candy bar that you can buy in grocery stores and gas stations. It's the Carmelo bar. It's got chocolate, it's got like these little camel humps, and you can break each piece off and there's Toblerone. Okay, Toblerone, yeah, there's those two. They're almost the exact same, right? Where the idea is that each of these, like that's the top profile, but when you look at it from the side, they're kind of like this. Each of these could be, like if you were to break it off, each of those could be a separate Platonic solid, right? But the problem is, this definition is trying to avoid that. So the idea is that this shouldn't happen. These are three individual closed spaces that are connected. That doesn't work. They want a single region. So a single region is something like this, where it's like an ice cube. where it's one solid mass of an object. It's not coming back and folding in on itself like the Toblerone candy bar or the Carmelo bar or whatever they are. Like it's one open area, so it's like a Snicker bar. It's just open on the inside. Everything's in the inside. It's not folding in on itself like these candy bars are. Okay, probably just made everyone hungry. All right, but the solid has certain names to it. So like the faces are the walls. We call those faces. So you can count how many faces are on that picture. There's a front, there's a back, there's the right, left, top, and bottom. So there's 6 faces on that picture. You can actually see them, they come highlighted then. It's really hard to show 3-dimensional. This room has faces. This room is, is some type of polyhedra, right? Because it has flat walls. So those are flat faces. It's got edges. Edges are the sides where the corners meet. So like this wall has, has an edge to it. The ceiling has an edge to it, right where the lines meet the corners. Then the vertices are the corner dots. So that'd be like the dots in the corners of the rooms. Okay, but it's solid, right? It's open, one open space. It's pretty easy to look at. The thing is that you need to know that we're not talking about planes anymore. We've stepped away from like infinite lengths to now definitive lengths where I can measure. These are measurable objects. So again, flat surface is called a face. We did that yesterday. The line segments connecting those faces, like in between the faces, are called edges. And then where the edges meet, that's a vertex. Objects do have bases. Just be aware of that. There's bases to objects, like the bottoms where they sit on. And that's something we're going to look at with some of these definitions. Like the base is kind of an important part of it. Okay. Questions with the things we did yesterday, what we talked about? Okay, I think that's where we ended, correct? We'd like to stop there. You want a liner?
Yeah.
I want those back today.
Alright. Also, I'm supposed to tell you to upload that level video from last night. They want to see Tori serve.
Okay. I'll get on. Alright. Now, I don't know if we got to this part here. The point where 3 or more edges meet, 3 or more. Notice it had to say 3 or more because we're doing a 3-dimensional object, so there has to be 3 axes that meet. Those are called the vertex. That's something, I didn't highlight that yesterday, I just talked about, where the corners meet. But it has to be 3 or more edges that meet to make a 3-dimensional picture. Length, width, and on depth. 3 sticks have to meet to make a vertex now, when you're in 3 space. In 2 space, like when we did squares, which is 2 walls. That was a part of the definition of a polygon. Every wall has to be connected to 2 or more. So 2 of them have to be connected to make a vertex on a 2-dimensional picture. You have a polygon. Alright, questions at all about the stuff from yesterday? I think that was new, I don't know if I had that one before yesterday. Okay, alright. Next, bases. This is the one thing I want to talk about today. Bases, there can be plural. So a regular polyhedron is kind of a special type of topic where the bases themselves, the faces, are regular polygons. So like on this picture here, on a regular polyhedron, all the faces are considered to be regular polygons, or they're congruent polygons. All edges are congruent, all walls are equal. So like on this one, you have 2 bases, okay, top and bottom, right? That one has 1 base. But a polyhedron is where every face has exactly the same wall lengths, the exact same angle measures. Every face is regular. Those are special. That's rare to see that, where you have every face being perfectly regular the entire time. And so this is what we're going to get into, like when we look at this. This idea of the regular polyhedra is when we get to the Platonic Solids. When you get to see when all the faces are exactly regular and you get to see what that looks like. Like this one doesn't look like it's regular. I can just tell you right now, this picture doesn't look, because these walls don't look like squares. They kind of look like rectangles. And that pentagon on the top and bottom, I don't know if that's a regular, we have to kind of measure those. But regular is one of the most special types of polyhedra. They're super difficult to draw and to look at because all the walls are equal, all the polygons are the same. Okay, questions with any of the basic terms? Now, if you go back up to the bases, if we look back up here, I talked about vertex and edges and faces, but the base on pictures, on polyhedrons, these bases are the parts that it sits on. Usually it's the two walls, but they always say it's the two walls that are parallel to each other, or the ones that it sits on. The base is actually how you name them, which is going to be kind of weird. So that's something you need to know. So like on this top one, when we name this, you actually name it by its base. Even though it is a pyramid, the base is a rectangle or square, so that would actually be called like a rectangular pyramid or a square pyramid. This one, this is a prism because it's not a pyramid, it's not coming to a point. You name it by its base. Well, its base is a pentagon, so it's a pentagonal prism. And that's something we're going to get to. I'll explain those definitions here in a second. So that's the base is the important thing. That's why I bring it up. The book doesn't really do a nice job of like explaining that. That's how we name the object, it's what it sits on. And I'll explain the prism idea here in a second. That's the next slide. Okay, we're good. Everyone's got everything written down? Perfect. Okay. So I actually didn't put that next. So the regular polyhedra, I didn't realize I put it this early. Regular polyhedra are, that's the thing where all the walls have to be regular. Okay. These are also known as the Platonic Solids. That's the cool fancy name for them. They're regular, so all the faces are, that's the definition you had earlier, so I just put it back up here again. All the faces are regular, congruent polygons. All the edges are congruent, all the angles are congruent. So here's the examples of polyhedra. There's 5 types of perfect Platonic solids, like where you have a perfect die. That's why you can't have certain sided die, because they're not perfectly balanced. Okay? One is called the tetrahedron. That's the first type of polyhedra that's a Platonic solid. That's where it has 4 congruent or equilateral triangle faces. 4 equilateral triangle faces. So here you go. So it looks like a pyramid, basically, but it's the first type of Platonic solid. You could actually make a die that's that shape, and it would be, all the triangles are supposed to be perfect equilateral triangles. So the base, and then the 3 walls up above. And there's 3 walls, so this is 4-sided. You've got this front, left, front, right, the back, and then the bottom. And they're all perfect equilateral triangles. They're all the exact same triangle, so they'd all be perfectly measured. So it's a 4-sided die you could have. Okay, questions with the tetrahedron? Second type, the hexahedron. Hexahedron. So now you're probably thinking, okay, hex is 6, so, and it's a cube. Well, it has 6 faces, right? 6 square faces. This is the traditional cube. That's the die that everyone's used to seeing. The one, I should say, 1 through 6, right? The 6-sided die. Perfect cube. Now I know, like in Vegas and wherever you go, if you're going to go and look at it, casino, they're always scared of people taking the die and like what they call is, it's called shaving it, where they mess with one of the walls a little bit. They shave off like a side of the wall just by hair, so it's off balance. So it always lands a certain direction. That's something that you wouldn't notice. It sometimes there's weighted die where they have weights on the inside and you would never see it. Even if the die is clear, sometimes they can fool you into showing it because it's not actually clear. It's like this weird plasticky material. That's why most casinos, when you actually see a die, they're actually clear. You can actually see your hand through it. That's how you can tell if it's weighted or not. If you can see your hand through, it's not weighted. But 6-sided hexahedron. Tetra is 3. It's a triangle basically. All right, octahedron. Well, you can get kind of an idea of that. An octahedron is 8-sided, right? 8 faces, but they're triangle faces, which is really weird. Here it is. It's kind of one of the harder things to show. It's actually 2 square pyramids put top and bottom. But you got to remember, it's every wall, all 8 of the walls are triangles, and they're perfect equilateral triangles. They're all the exact same triangle, but it's 8-sided. So the distances make a big difference. So like how tall it is, how wide it is, they all have to be perfectly symmetrical. So you can lay in any face. So there's 8 equilateral triangles. The fourth one, while you guys are just starting to scramble to get these down, the fourth one is a dodecahedron. Well, what's dodeca mean again?
12.
12, right? So this has 12 pentagonal faces. It's like a princess cut diamond, right? It's round, blush, kind of a round cut diamond. But this is really hard to see. This is a top-down view of a dodecahedron. Every face is a pentagon. I've tried to go to a top-down picture of it because you can see like the pentagon on the top, but every wall is an actual pentagon. So you have the top, and then you have 5 that go around it. So that's just the top half. If you were to flip the object over perfectly, like this is perfectly top, if I were to flip it over, it has that top and then 5 pentagons that go around it as well. A soccer ball is not, a polyhedron, or a regular polyhedron. The reason why, if you ever looked at a soccer ball, the faces are not all the same. Some are pentagons, some aren't. You have to look at kind of the shapes of it. So it's not a perfect polyhedron. And it's kind of rounded too, but you get the idea that they're flat. Fifth and final one, the icosahedron. Icosahedron is 20 equilateral triangles, and this is your 20-sided die that we talked about. So the last one, 20 triangular faces. Here it is, a 20-sided die. I'm not even going to attempt to explain how to look at that. It's triangle faces. There's got to be 20 of them. I don't even know how to count that. I'm not even going to attempt to count that. I can't even see it. That's like, you know how people say like they can't see 3-dimensional. I can't even attempt to see what that thing is supposed to look like. So I have to like physically see an example in my hand, because I can't tell if all that white and blue. Like the dodecahedron, I can see it. Like that's top down. This thing, they're trying to do 3-dimensional. I can't see it. The dash lines are really throwing me off. Especially that white in the middle. I just can't see that. Everything else is pretty straightforward. Okay, do we understand what the polyhedras are? Now after this, these are like the main 5. After that, they get so out of control that you can't see it, like it's too many faces. But you're starting to see like what they usually use. They use triangle faces for the most part. The ones in between use pentagons, hexagons, or pentagons I should say. The next one, if I was following that same pattern, because if you notice, like it's every other, and it's going up, it's going, 4, 6, 8, 12, 20. Like this is a sequence, that's something we'll talk about. There's a sequence there of how many faces there are. The next one, if I was logistically thinking about what the next type of regular polyhedra or Platonic solid, I can figure out the number by using this pattern, where it's going up by certain numbers. But the next one I would assume would be using hexagons, because it's going up. The one after that would use triangles again. Then the one after that would be a heptagon, and then it would be a triangle again. And so like it's going, every other is use triangles, and the ones in between are going up. It's going from a quad to a pentagon to a hexagon to every other. But then the numbers of the faces, you'd have to look at like what it's jumping by. Well, this one jumped by 2. This jumped by 2. This jumped by 4. This jumped by 8. There is a pattern there. Believe it or not, there is a pattern that it'll actually get you to the next one. Okay, questions, comments about the polyhedrons, the regular ones? Those are the rare ones. Like that doesn't happen very often. The cube is probably the most common to everybody. A lot of people probably didn't know the pyramid was one of them, the triangle pyramid. Alright. The types of solids. Now, these are not regular. These are any type of polyhedron that you can have. So just the regular types. You can have prisms. Prism is one of those things I was going to warn you earlier. I didn't realize I put the regular ones before this. The regular polyhedra, or the just normal types of polyhedron, I should say, not the regular, but just the types of polyhedra. Prism is the first one. It's a polyhedron where the two walls that are parallel to each other, that the faces are congruent, the parallel walls that are congruent faces, those are called the bases. So the bases are the walls that are parallel and they're the same wall. They're exactly the same dimensions. That's how you name a prism. So you name it by its faces, by its base that is parallel. So there's different types of prisms. Like this one is called a Pentagonal Prism. Because it's pentagons that are the ones that are parallel, they're equal, so you call it a pentagon, and then there's a prism after it. And there can be any type of prism like that. There's the pyramids. Pyramids look very, very different than prisms. And there's another definition of prisms. They use rectangles for the walls usually. But pyramids go up to a pike. You go up to a point. It's a polyhedra where there's a polygon for a base, a regular polygon, right? So it could be a triangle, it could be a square, a pentagon, a hexagon, an octagon, any of those. But if the other wall that's not the base goes up to a point. So something like that. So this picture, you name it by its base, so that's called a square or rectangular pyramid. As you look at its base and when it's going up to the point. Question?
Okay. For the pyramids, does it have to be a triangle to go up to a point?
Yes, they use triangle faces up to a point for the pyramids. Yep. So like on the prisms, they use rectangles for the other walls, but on a pyramid, they use triangles. And it can be any base. Like when I'm talking like a pyramid, they could be some weird pyramids. Like one of the ones in the book, I think it actually gives, let's see, is that 6? 1, 2, 3, 4, 5, 6, yeah, that's 6. A 6-sided pyramid, so it's a hexagonal pyramid, where this goes up to a point. Is that my phone? Mr. Ward? What's up? Yeah. We're in like 74 pounds, because people I didn't get weigh-ins this morning. So I need them to the average rule. Have to be, so they have to be delayed. 374. Okay. Okay, bye. Alright, sorry. Alright, so if the base is a hexagon and it goes up to a point, it's called a hexagonal pyramid. Okay? Alright. This is our last slide here. Okay, last slide. Let's get to these other types here. And the types of solids that are not polyhedrons. So these are not, they're solids, don't get me wrong, it's a three-dimensional object, but they're not polyhedrons because they don't use flat walls like triangles or quads or anything like that. The ones that are not polyhedron are the types of conics. So in fact, I didn't even put that word up here. These are what they call the conics. The conics. It's the type of like circular objects. They use circles or curved edges. Cylinder is one of them. Okay, it's a solid where the congruent parallel circle bases, parallel circles, they're congruent circles, and they're connected by a curved surface like that. Circles top and bottom. It's like a pop can or a water bottle. But the top and bottom are exactly the same size. And there's just a smooth edge connecting. It doesn't bow outwards. That's a cylinder. There's the cone, where it has a circle base, but it goes up to a point, a single vertex, a singularity. So curved surface to a singular vertex. Something like that. So it's got a circle base, so it's like an ice cream cone. And then the last one is a sphere. A sphere is basically all the points that are congruent or equidistant from a central point. all, the set of all points that are equidistant from a set location in the middle, central point. So if you had a center, and you went any direction you wanted from that, that'd be a sphere. The Earth is not a perfect sphere, believe it or not. The Earth is actually flattened more north and south than it is east and west. East and west has been pulled, elongated. The sun is actually stretching us like a football, basically. It's very, very small. It's just maybe 100 miles or so, which on the Earth standards is nothing, because the Earth around is like 26,000 miles. But it's stretching us just slightly because of the equator and where the sun is actually pulling us on the disk, the plane. I think one of the best movies I've ever seen explain a sphere. The sphere is, where's that space movie? Yes? Sure. Yeah, whenever you know. That'd be great. Alright, but there was a movie that came out with Matthew McConaughey 2 years ago. It was based on, what was that movie? It was really good too. I'll figure it out for tomorrow. But in the movie they talk about time travel and wormholes, Eisen bridges, where there's a wormhole in space, and the wormhole would actually appear as a sphere to us. Because in space it's not two-dimensional, it's three-dimensional, and so that circle where the actual wormhole would open would be a perfect sphere. It would be equidistant from all edges, which is actually a really perfect way to explain it. Scientists actually believe that, a wormhole does exist, that you can actually enter one and it would actually, be a rip in time and space. It would transport you. But it would appear as a sphere in space. It was just this really cool 3-second clip of this movie that actually did a really nice job of explaining what a sphere is and why it would be that way in space. I'll find the name of the movie. But alright, that's our last thing today. That's all I wanted to cover. Pretty easy.